first focus on this. Okay, we will just have a quick recap. Okay, so you already know that if we have a Z transform, okay, most probably it is a ratio. No, it is a ratio. Okay, so we have is this denominator, okay, and we have a numerator. Okay, I think the this one is the numerator. No? This is the numerator, and also we have a denominator. Denominator. Okay, so this will be our denominator like this. Okay, let's check it. Whether my words are correct or not. Okay, the no, denominator and numerator. Yeah, okay. The above number is the numerator, and the lower the bottom number is the denominator. No, numerator and denominator. Okay. So if you consider a Z transform, if we consider a Z transform of a time series, most probably it is a ratio. Okay, it is a rational function. Okay, it is the rational function. It is a rational function. Okay, and it have numerator and denominator. Okay, denominator. Okay, like this. Okay. So you can see that. Okay, so it has a numerator. Okay, and it has a denominator. Both are Z function. Okay, both are Z function. Okay, so here I clicked in wrong direction. No, so here we have a numerator, and here we have a denominator. Okay, okay. So this is the numerator, and this is the denominator. Okay, so this is a rational function. Okay, xz can be expressed as a ratio of two z function. Okay, two function of z. Okay, so this is the function of z, and this one is also a function of z. Okay, so if we equal our numerator to 0, okay, and if we solve the value for z, okay, solve the value, okay, if we solve for z, okay, so those values are zeros. Okay, those values are 0. Okay, and if we equal the denominator to 0, okay, and if we find the z values, okay, corresponding z values, so that z values are the poles. Okay, in another word, okay, in another word, if we have a z transform, okay, if we have a z transform, and z transform is a rational function, then z be z. Okay, and if we equal this nz to 0, that means our z transform is also limiting to 0. Okay, and if we found that z, okay, if we found that z value, so there may be different z value. Okay, for that z value, our z transform is limiting to 0. Okay, so those are called zeros. Okay, and if this denominator, if we equal this denominator to 0, that means xz will become infinity, no? Infinity. Okay. So z values that reach our, so there may be z values, several z values. So for those z values, this xz will be reaching to infinity. Okay, and those are called poles. Okay, so these are the zeros and poles. Okay, in zeros, our z transform is limited to 0, and in, at poles, okay, at poles, our our uh, our is a transform is limiting to infinity. Okay, so these are poles and zero. Okay, so we have our complex plane. Okay, we have our complex plane like this. Okay, okay, so this is the imaginary of z. Okay, and this is the real of z. Okay, so this is the z plane. Okay, so this z, okay, if we consider any Z transform signal, okay, Z transform sequence, okay. Um, so the value of Z, okay, value of Z that exists is called as the the region of convergence. Okay, so different signals, different sequence, okay, will have different region of convergence. Okay, okay, okay. So uh, so if we equal this xz to 0, and if we find the z value, okay, z value, those z values are those z values also in this z plane. Okay, also in this z plane. Okay, so we can plot that z values. Okay, z values, z values, z values. Okay, okay, so we have our z plane. Okay, so we have our z plane. So this is imaginary part, imaginary of z, and this is the real part of z. Okay, so if we if we have it's a transform sequence, and if we so we have so this will be most probably a rational what is called the rational function. So that means we have numerator and denominator. Okay, so if we equal this numerator to 0, okay, if we equal this numerator to 0, then xz also will be 0. Okay, so if we found those z value, okay, z value, okay, so these are zeros, those are zeros. So these zeros, the value of z, okay, so those can be real numbers. Okay, so this zeros can be real number, can be real number, or maybe it may be complex number. No, it also may be complex number, we don't know. Okay, but anyway, we should be able to, okay, so these are should be in this z plane. No, okay, so it may be any place. Okay, so normally we denote a pole using this notation, this symbol. Okay, so if we have mark the zeros, okay, on this z plane, So it will be look like this. Okay, still we don't know what are the value. Okay, so I just mark arbitrary zeros value. Okay, okay, and in the same way, okay, in the same way, if we have, if we have, if we have uh, if we equal this denominator, okay, dz to 0, okay, then xz will become infinity, okay, and we equal this dz to 0, denominator to 0, and if we find the value of z, okay, value of z, okay, so you can understand that for that values, okay, so that values also can be real or imaginary, okay, we don't know, real or complex, okay, real or complex, we don't know, okay, but those are also should be in this z plane, no, so for that z value, this xz will be reached to infinity, so we called them poles, okay, we call them poles, okay, so we will have poles, uh, we uh, it can be have, it is possible to have uh, the poles at any point of this z plane, okay, so normally we denote the pole using a cross like this, okay, so if we have some poles, okay, so those poles also in this z plane, okay, and we can denote it, we can mark it using the cross, okay. So in this z plane, we have plot the zeros, okay, so these are 0, and also we have plot the poles, these are poles, okay. So this is called pole 0 plot, okay, this is called pole 0 plot, okay. I hope you you have a, now you have idea what is a pole 0 plot, okay. So what we are doing here, we just equal the numerator to 0 and find z values, okay, so those z values are 0, okay, so we can mark them on the z plane, okay, and if we equal the denominator to 0, okay, so the values for z we get, those are called poles, okay, and we can mark the poles also in the same z plane, okay, so that is a pole 0 plot, okay, so I think now you have idea about the pole 0 plot, okay, so we will later we will see what are the advantage of pole 0 plot, okay. I think you have already know that if you learn Laplace transform, I think you have searched the poles and zero, okay, poles and zeros, okay? And using the pole zeros plot, we are mainly conclude that a system is stable or not, okay. So we normally use pole zero plot to see a signal, to see a system is stable or not, okay. So we will see it. We will see them later. Now just have an idea about the pole zero plot. Okay. Okay. So so if we move further, okay. So you have a table, okay. So that is the properties of Z transform, okay. So there are many properties actually, but we are not hope to discuss all the properties, okay. We will discuss some important properties only, okay. So I hope to discuss this linearity property, time shifting property, I think this one also may be also important when we are uh, analyzing uh, systems. Okay, uh, normally uh, linear time invariant systems. Okay, LTI systems. Okay. So anyway, we will keep this later. Okay, and I think we have to study the time reversal also. Okay, and I think one this differentiation property. Okay, differentiation property is also a important property when we are analyzing uh, when we are analyzing a system in Z domain. Okay, and convolution property. I think this one is very important. Okay, this one is very important when we are analyzing a LTI system. Okay, so at this point, okay, I will I expect to cover uh, at least this 1, 2, 3, 4, 5 five properties. Okay, 5 properties. Okay, so if we have time, we will see another important 2 or 3 properties. Okay, anyway, I think these 5 properties are most useful and mostly used properties. Okay, maybe I am wrong. Okay, maybe I am wrong. Okay, but according to my experience, okay, I am also not expert on this is a transformation uh, things. Okay, uh, so according to my understanding, I think these properties are important, and we come across these properties very often. Okay, so we will see. Okay, one by one. Okay, so in this section we will try to cover at least linearity property and time shifting property, these 2 property today. Okay, then after that we will try to cover these 3 properties. Okay, so if I go to the linearity property. Okay, linearity property, so it is very simple actually. Okay, so this is the linearity property. Okay, okay, so if we have xn signal time series. Okay, and the is a transform is sorry. Okay, sorry. So if we have a x1 n time sequence. Okay, and it is a transform is x1 is at. Okay, and if we have x2 in sequence, is a transform is x2 is at. Okay, so here the ROC is ROC1 and ROC is ROC2. Okay, let's say like that. Okay, so if I weighted this signal some scalar with some with the scalar. Okay, if I weight this signal with some with a scalar value, let's say a1 and a2, and if I add those together. Okay, those 2 terms together, and Z transform of the resultant signal. Okay, so this is the composite signal, no, added signal. Okay, so 2 signals are added together. Okay, and I will have this. For Z transform, I will have this. Okay, so if I separately weighted the corresponding Z transform with the corresponding scalar. Okay, and add them together, I get the resultant signal Z transform. Okay, so this is very simple and very straightforward property. Okay, okay, so So if we consider the ROC, okay, it says that at least the region 1 and region 2, intersection of region 1 and region 2 should be there. Okay, so we will see a example and try to get a good understanding. Okay, so here another thing I want to tell you. Okay, so you can see that there are many solved questions. Okay, there are many solved questions. Okay, so I will try to uh, do that solved question. Okay, really. Okay, I will minimize. I will try to do. Okay, try to do other problem as much as possible, because these examples are already solved. Okay, so you may be able to understand them by yourself. Okay, so please try to understand, try to do those examples at least, and try to get understanding how to perform this is a transform and how to find the ROC. Okay, meanwhile I will be mostly focusing on the problems. Okay, problems given in your note. Okay, so there are many problems actually. Okay, so I think already you can do this kind of questions without issue. Okay, and also I hope you can do this kind of signal, this kind of one also without issue. Okay, okay, so we will try to do another question. Okay, so and we will try to apply the linearity property also. Okay, so I think if you select this question, okay, if you select this question, I think we can do it. Okay, so we will try to do this. Okay, so we have a signal. I think we can copy it. Okay, so this is a signal. Okay, and so we will try to do this. Okay, so so first try to do this by yourself. Okay, try to do this by yourself. Okay, and after doing that you can check that with my answer. Okay, with my answer and my procedure. Okay, so here you can see that I think this is not okay, no? So I will write it here. Xn is equal to an plus a minus n un. An plus a minus n un. Okay, so it is said that a is the real value. A is the real value. Okay, so sorry, the simple a is a real value. Okay, but it is not said that a uh, a uh, a is greater than 1 or a is less than 1, less than 0, greater than 0 or less than 0. Okay, it is not said. Okay, so we will see how to find this kind of question. Okay, so before starting this question, okay, I will tell you one important things. Okay, so when we are dealing with time sequence, okay, when we are dealing with time sequences or time series, you can see that when those time series are mathematically shown using the equation, okay, so many times you can see that the signals are multiplied by this unit step function. Okay, okay, so what is the use of it. What is the use of it? Okay, so what is the use of it? So we will see. Okay, we will see this. Okay, so here, okay, so here, now I am going to use the linearity property. Okay, so that is my uh, linearity property. So that is my aim. Okay, so I'm going to use the linearity property. Okay, which we have learned previously. Okay, so if I remove this bracket, okay, so it is a n u n plus a minus n u n. So I have two signal added together. Okay, but it is not weighted. Okay, it is weighted by 1. Okay, it is weighted by 1. Okay, so anyway, it is also a weighted 1. No, it's weighted by 1. Okay, so we will see. Okay, so so this is still not given. Okay, an, so let's say that this is x1 n, and let's say that this is x2 n. Okay, okay, so this is x1 n and x2 n. Okay, so let's try to find x1 n, x1 n. Okay, so we will try to find this x1 n. Okay, can you give a try by yourself? Okay, so we have x1 n equal to a n u n. Okay, just try, just pause the video and try yourself, then you can see the procedure, my procedure. Okay, so we will try to see this. Okay, so we were talking about the matter of this UN. No? Okay, what kind of impact done by this UN to the signal? Okay, so we will see it. Okay, so if I draw this UN, okay, if I draw this UN, we know that it is starting from 0. Okay, and if it is not weighted, we have 1. Okay, at 0 we have 1, at 1 we have another 1, 2 we have 1, 3 we have sorry, 3 we have 1, and 4 also we have 1. Okay, and this is goes up to infinity. Okay, so 0 1 2 3 up to infinity, 3 4 up to infinity. So we have 1 1 1 like this. Okay, so this is the unit step function. Okay, so you can see that this is a partial signal because we have only plus-sided value. Okay, because we have only plus-sided value, and this also infinite sequence, infinite series. Okay, so this is the infinite series. Okay. Okay, so next we will try to draw this signal also. Okay, this signal also, this sequence. Okay, an. Okay, so I just forget about this un. Okay, I just forget about this un and I'm trying to draw the an signal. Okay, so n, so here we have no any restriction. No, for un we know that there is no minus infinity, the minus values. Okay, so it is start from 0. Unit step function is start from 0. That is how it defined. Okay, is how it defined. It is starting from 0, no minus value. Okay, but this an, we don't have such a specification. No. Okay, so this an n, okay, can be minus infinity to plus infinity, any value. Okay, so it can be minus infinity, minus 5, minus 4, 3, minus 2, minus 1, like that. Okay, and also it can be 0, 1, 2, 3, 4, like that. Okay, so let's say that So if we try to draw this signal, so this is also infinite sequence. Okay, this is also infinite sequence, but it is non-causal signal, non-causal signal, non-causal signal, because it has both side, this side and this side. It is a two-sided signal. Okay. So if we try to plot this, okay, we can't plot all the values because there are infinite number of impulse. Okay. So we will draw few values. Okay. So we don't know this A. So we know that this A is a real value. That is the only thing we know. But we don't have idea about A. Okay. Let's say that A is greater than 1. Okay. So this is not important actually. For our question, this is not important. But if we are drawing the signal, this will be important. Okay. So if A is greater than 1, okay, so A0 will be 1. Okay, A0 will be 1. A1 will be a value like this. Okay. So this is 1, 2, 3. Okay. A2 also will have a value, the greater value than this one. So that is A2. Okay. And this one also have a greater value, that is A3. So I write it here. Okay. Okay. So we have N and we have Xn. Okay. Xn. Okay. So we don't know the in value. So it can be plus infinity to minus infinity. Let's say it is -3, -2, -1, 0, 1, 2, 3, so on up to infinity, and also and here also up to minus infinity. Okay. So now consider that A is greater than 1. Okay. So A0 we have 0. So this is An. Okay. An. That means 0 means A to the power 0, that is 1. Okay. And here A to the power is square. So A is square. So if it is greater than 1, so it is greater than this value. Okay. And if it is 3, N is 3, it is again greater than this 3. And it is 4, it is again greater than this one. Okay. So it will be go like this. Okay. Okay. And if it is A minus 1, so it will be less than 1. A minus 2, okay, A minus 2, and also it will be less than this one, and A minus 3, so on. So we have an exponential distribution actually like this. Okay. Okay. So this is An. Okay. And if A is less than 1, so this curve will be vice versa. No, it will be like this. Okay. So if A is greater than 1, okay, if A is greater than 1, sorry, I have a mistake. Okay. So this curve is for A is greater than 1. Okay. So this curve is for A is greater than 1. That is why A0, 1, A is square, it is less, it is more than 1, and A third, it is A to the power 3, and it is also bigger, greater than this value. Okay. So it is A this A is greater than 1. Okay. Okay. So it happened when the A is greater than 1. Okay. And what happened if A is the decimal value, half value? That means if it is A is less than 1 and greater than 0. So this A is between 0 and 1. That means it is a, what is that called? It is the decimal value. Okay, it is a decimal value. Okay, it is not greater than like this. Okay, so if it is so, the value distribution will be like this. Okay, so different A value will be get different pattern. Okay, but it is not impact to our signal. Okay, so you can see that these two signals are multiplied. These two signals are multiplied. So when we multiplied, what happened? Okay, so if these values are 0, minus infinity to up to 0, all value are 0. So all values from minus infinity to 0 in an will be cancelled out. Okay, okay. As a result, we get only 0 to plus infinity value. Okay, only 0 to plus infinity value. Okay, so other value will be reduced, will be cancelled out, disappeared. No. Okay, so you can see that. Okay, so multiplying this signal by un is not going to change anything. Okay, but the range of this n, okay, so actually it become a causal signal now. Okay, it become a causal signal now. So by multiplying the value with this value un, okay, with the unit step function, it is a information about the range of n. Okay, now it is 0 to minus infinity, plus infinity. Okay, so it is just an information about this n range. There is no any input. Okay, so that is the idea you should get. Okay, so if a is greater than 1, okay, if a is greater than 1, or it may be a half value. Okay, anyway, if this is n, if this is xn, okay, we have 0th one 1. Okay, then we have a1, then we have a2, then we have a3, so on up to infinity. No, infinity. So if I write the z transform for this, what will I get? If I write the z transform for this infinite sequence, what will I get? I will get, okay, I will get, so you know that xz is equal to n minus infinity to plus infinity xn z minus n. Okay, so this is the z, the definition of the z transform. Okay, so xz will become, okay, so for this sequence n is from 0 to plus infinity only, not minus value. It is for 0 to plus infinity. Okay, so we have here a0. Okay, n is 1, n is 0, so we have a 0. Okay, a0. So here the xn is an. Okay, so if I write this for our case, so it will become n 0 to plus infinity. Xn means an z minus n. Okay, so this is the z transformation I get. Okay, so if I expand this, I will have the n is equal to 0. That means a0 z minus 0 plus, if the n is 1, a1 z minus 1. If the a is at 2, a2 z minus 2. If the z if the n is 3, if the n is 3, so we will have a3 z minus 3, so on up to infinity. Okay, so what is this actually? So this is the infinite series. So it is not infinite infinite just a series. Okay, it is infinite power series, no, infinite power series, or maybe it's a geometric series. Okay, so if I write this further, we will have so a0 is at 0 means 1 plus a by z plus a by z is square plus a by z to the power third up to plus infinity. So I will get this kind of power series. Okay. So when the power series are there, okay, Taylor should also be there. Okay. So this one also we can represent as a Taylor expansion, Taylor series. Okay, as a compact form. Okay. So it is also 1 plus so here in our book it is called a, no, a plus a square plus a to the power 3 plus up to infinity. You can write it as 1 by 1 minus a. Okay, and there is a condition for this a, the magnitude of this a should be less than 1. Okay, so this is one of a Taylor series, Maclaurin series. Okay, so we can use this one to get this as a compact form. Okay, so I write it x z. Okay, so we can have a 1 plus 1 minus, so instead of this a, it is a by 2, no, it is a by 2, a by 2. Okay, sorry, a by z. Okay, sorry, I'm sorry, a by z. Okay, this is a by z. Okay, so now it is 1 divided by 1 a by z. Okay, z. Okay, so this is the z transform. Okay, and this is this magnitude of this a z should be less than 1. Okay, so if I go further, I can say that if we do the cross product, the magnitude of z should be greater than magnitude of a. Okay, so we have this result. Okay, so I think you can already get this kind of result. Okay, so z is greater than me. Okay, greater than square. So if I get the z plan. Okay, so this is imaginary z, and this is it's called real z. Okay, this is a real z. Okay, and if we draw this, okay, so magnitude of z. Okay, so magnitude of z is uh, like this. Okay, like this. Okay, so if we get any point, so it will be the magnitude of z. Okay, like this. Okay, and magnitude of the z should be greater than a. Okay, so if the a is here, okay, if a is here, so all these values are not in the region of convergence. Okay, except this except these except the values inside these circles. Okay, other all values we can get as z values. Okay, so for that values z transform will be converged. Z transformed value will be converged. Okay, okay, now consider our, so this is our first one. Okay, so consider our second sigma. Okay, what is that? It is a minus nun. Okay, a minus nun. Okay, correct. Yeah, it is a minus nun. Okay, so I think in the same manner like we did here. Okay, there is no any difference. Okay, so both are same, so I'm not going to do this. Okay, so you can see that if we find this one also, okay, you will get xz, okay, xz, okay. So if I write the xz, so here a minus n, okay. So it should be from n also, because it is multiplied by un, so n also should be 0, from 0 to infinity, okay, from 0 to plus infinity, okay. So these n's are available only, okay. So if n is 0, we have a0 z0, plus if n is 1, we have a minus 1 z minus 1, plus if n is 2, we have a minus 2 z minus 2. If a is 3, we have a minus 3 z minus 3, so on. Okay, so this also power series, okay, and it will become 1 by a minus 1 z minus 1, that means 1 by a z, okay. So this is the x2 z, okay. And in the same manner, okay, in the same manner you can find the ROC, okay. In the previous case, uh, the magnitude of z is greater than magnitude of a, okay, magnitude of a, okay. But here a is there, a is here, but now instead of a we have 1 by a, no, 1 by a. So you can replace here also. The magnitude of z is greater than 1 by a, okay. So I think this also you can do by yourself, okay. So I hope you get it, okay. So if I tell the summary, okay, so we have two signal x1n, okay, and if we get the z transform, we have xz, and xz is equal to a 1, sorry, 1 divided by 1 minus a z, okay, and the ROC, region of convergence, is z is greater than a, okay, z is greater than a, the magnitude of a, okay. And we have another signal x2n, okay, and if we get the z transform, it will be x2z, okay, and it is equal to 1 by 1 divided by az, okay. So this is the second signal, and ROC is equal to z is greater than 1 by a, okay. So we have these two signals, and what we have to find, we have to find if we have to find xn, okay, that is equal to x1n plus x2n, okay, and it is weighted by 1, okay. So we have this signal, this is a transform, we have this a transform of this signal, and we have this a transform of these signals, okay. So using the linearity property, it tells that if we get the z transform of this signal, xz will be equal to the z transform of x1, that is 1 minus a z, okay, and weighted by 1 again, okay, plus x2n is a transform of x2n, that is x2z, okay, x2z. So okay, x2z, that is 1 by 1 a, sorry, az, 1 minus 1 by az, okay. So this is the x2z, and it is also weighted by 1, okay. So this is the z transform, and I use the linearity property, okay. So linearity property is, before come to this, okay, there is another step. So xz will be equal to 1, the weighted value, x1 z plus 1 x2 z. Okay, then the next step is this one. Okay, so this is the x z. Okay, so now what is the r z? Now what is the r z? Okay, so you can see that. Okay, you can see that. Okay, for x1 z, ROC is like this. Okay, okay, if this is a, ROC is greater than this a. Okay, like this, all value. Okay, and x2, if I write the x2, okay, so this is x1. Okay, this is x1. Okay, if I write the x2, okay, if I draw the x2 in x2 z, okay, ROC should be 1 by a. Okay, 1 by a. So it may be like this. It may be like this. Okay, so it is 1 by a. Okay, but it is 1 by a if a is a is greater than 1. Okay, if a is greater than 1, okay, it greater than 1, this a by 1 is inside the a. Okay, but what happen if a is a rational, sorry, is a decimal number, that means 0 to between 0 and 1. Okay, decimal number, let's say it is 0.5. Okay, so now a is 0.5, and what about 1 by a? It is 2. Okay, so in that case, okay, in that case, the 1 by a will be outside this a value. Understand? Okay, I hope you can understand like this. Okay, so this is the 1 by a again. Okay, so here the a is between 0 and 1. Here, for this case, if 1 by a is inside the a circle, that means a is greater than 1, this case. Okay, did you get it? Okay, I will draw it again if you are not, if it is not clear, the diagram. Okay, now, okay, I will write this also. Okay, to get to have a better understanding. Okay, so now we have x1 in. Okay, if we get the z transform, we have x1 z, that is equal to 1 by 1 a z. Okay, a z. Okay, and ROC is z greater than magnitude a. Okay, and we have x2 in. If we get the z transform x2 z, we will have 1 by 1 by a z. Okay, and ROC is z is greater than 1 by a. Okay, so I get this. Okay, so now I am going to draw the ROC. Okay, so here my imaginary value, and here my real value, real axis. Okay, so this is imaginary axis of z, and this is real axis of z. Okay, so if I mark the ROC for first case, okay, for first case, I have z greater than a. So if I draw a circle with a radius, okay, so this is the magnitude, no? So this is the magnitude of z, and that magnitude is greater than a. That means this area. Okay, greater than a means this area. Correct? Okay. Then I have this this ROC, except inside the values inside this circles, other values, all other values are inside the ROC. Okay, so this is x1 z. ROC for x1 z. Okay, x1 z. So if I draw the x2 z in this z plane, okay, what I get? Okay, so if a is greater than 1, okay, that means a can be 2. Okay, if a is 2, so a is 2, but 1 by a is half. So all the values, this 1 by a will be inside this a circle. Okay, you get it? Okay, so that is x2 z. Okay, but say that a is between 0 and 1. Okay, so this is for this condition. Okay, so let's say that so this is here. Okay, so let's say that a is a rational, not rational, it is a decimal value, 0.5, 0.3, 0.4, so on, like that. Okay, so let's say that 0.5, so a is 0.5 and 1 by 0.5 is 2. So in that case, if a is between 0 and 1, okay, x2 will be the value, the ROC of well, x2 will be outside this A circle. Okay, outside this A circle like this. Okay, so you can say that for both signal, we have to get the values after than the big circle. Okay, big circle. If you consider the value here, so for this for x2 z, okay, sorry, x1 z, so it is not converged, that means it is in unconverged. So you have to get the other values, okay, for the ROC. Okay, so I hope you get it. Okay, so if you have these two signal, x1, so if you want to get the x z, okay, that is x1 z plus x2 z. Okay, so you will have 1 by 1 minus a z plus 1 by 1 minus 1 by a z. Okay, okay, so the ROC for this, okay, RO for this, ROC, okay, the z should be greater than greater than magnitude of a. Okay, if a is greater than 1. Okay, did you understand this? Okay, that is what I explained. Okay, okay, so here I will draw. Okay, z plane. So this is how z plane. Okay, so ROC for this signal x1 2, that is this. Okay, this is a. Okay, and ROC for this signal, let's say it is like this inside this a. Okay, so that means a is greater than 1. Okay, so that is why this is seen. Okay, let's say that a is 2, so a is equal to 2, but 1 by a. Okay, 1 by a, here the for x2 signal, the ROC is Z should be greater than 1 by a, not a, 1 by a for x2 signal. Okay, so this is for x1 signal. Okay, so if the a is less than 1, so the Z value will be inside this a circle. Okay, okay, so for this one, the second signal ROC is this one. The first signal x1 1 Z, the ROC is this one. Okay, so these region the beyond this a value are common. The values common, those values are common for both x1 ROC and x2 ROC. Intersection actually. Okay. Intersection, no? Okay. So those common values are the ROC. Okay. So if A is greater than 1, ROC will be greater than A. Okay, greater than A. But what happens if A is 0 and 1? What happens? Okay, so this is A. Okay, and 1 by A will be outside the A circle. So this will be 1 by A. Okay. So at that point, at that time, if A is between 0 and 1, okay, so for x1, okay, ROC is this area, okay, and x2 ROC will be this area outside this circle, okay. So what is the common area for both signal, both term? Outside this capital A, no, outside this this big box, that is 1 by A. Okay, so in that case, the ROC is the Z value. ROC is at the Z value greater than 1 by A. Okay, 1 by A. So this is what you have to understand. Okay. Okay, so we get the common intersection of both ROC. Okay. 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 So we have xz as 1 by 1 A by Z plus 1 by 1 A Z. Okay. So please try to understand by yourself also what about this story. Okay. How the ROC we find. Okay. So we will do another example also, and we will try to minimize the if you have any confusion, we will try to minimize the confusion. Okay. So anyway, if you try this by yourself, I think you can understand. Okay. So now I am going to find the poles and zero. Okay, poles and zero. Let's see how to find the poles and zero. Okay. So before that, so this is A by Z. So this is 1 A Z. Okay. So if I write this, I will have, if I further simplify this, so this Z, if I get this Z for common denominator for both the terms, so I will have 1 Z minus A, and this Z will go up, so I will have Z minus A plus, in the same way here A Z will come, so here A Z minus 1. So these two terms I will get. Okay, then we have to solve this again. We have to simplify this. So I get the common denominator, that is Z minus 1. Okay, so here we have Z minus 1 plus Z minus A. Okay, so if I further simplify it, okay, Z minus 1. So here we have Z square. Okay, so Z square minus Z plus, here also get Z square minus A square Z. Okay, so if I get Z, okay, so here A Z square, I will have 2 Z square. So all terms have Z, so I get out 1 Z. Okay, so here we have A Z square, 2 A Z square. Now we have 2 A Z. Okay, because 1 Z is outside the bracket, and minus So z is now, we take a square plus 1. Okay, so we will have this. Here we have z a, so z minus 1. So what we have to first do? Okay, so this is our xz. Okay, so we have write it as a rational function, no? So we have a numerator and we have a denominator. So what we have to do? We have to equal this nz to 0. That means this this value, so you know that a is real. Okay, it is given. Okay, so if you equal this upper part to 0, that is z 2a z minus a is square 1, okay, equal to 0. So this z can be 0 or this can be 0. Okay, so if this can be 0, z a in a 2a z minus a square minus 1 equal to 0. So we will have z as a square plus 1 divided by 2a. Okay, so this is the z. This is another z value I get. Okay, so here z I have 0, so that is one pole, and this is also a pole. Okay, so what about 0? To find the 0, sorry, these are the zeros, no? These are not poles, these are zeros. So this is one pole, 1 0, and this is another 0 point. Okay, for both these value, the nz, the denominator, numerator will become 0. Okay, so what about poles? To find the poles, we have to equal this part to 0. Okay, so so these are zeros. Okay, and to find the pole, to find the pole, okay, I also equal these two terms. So z minus a z minus 1. Okay, so z minus a can be 0. That means z equal a. Okay, and a z minus 1 also can be 0. That is z equal 1 by a. Okay, so for above signal xz, there are two zeros, 0 and at this point, and there are two poles, z equal a and z equal 1 by a. So if I plot the pole 0 plot, it is something like that. Okay, so here we have real part, and here we have imaginary part.